Hello, here's some more practice questions in astronomy and cosmology, starting with a nice simple opener, state Hubble's law. Right, we should be pretty slick at this by now, but we will say that the recessional speed of a galaxy, and it's important to mention galaxy because we need to show that we know that this is not to do with objects within our own galaxy, the Milky Way. It's to do with objects outside of our own galaxy. So recessional speed of a galaxy is proportional to its distance from the observer. So that's a nice way to kick us off on this set. Second part, part B, the dark lines of a spectrum observed from a distant galaxy are redshifted by 15% of their normal wavelengths. Hubble constant is 65 of the normal units, and then that's the number of meters in a parsec. Show that the speed of the galaxy is that. So they've given us, if we go to our Doppler equation, they've given us the delta lambda over lambda bit of it, said that that's 15%. So that's our 0.15, and then that is V over C. So nice simple calculation there to get what V is. It's just 15% of C. So we've got 1.5 multiplied by 3 times 10 to the 7, which is 4.5 times 10 to the 7 meters per second, which is what they wanted us to show. Estimate the distance of the galaxy from Earth. Now we can bring in our Hubble's law because V is h0 times d. So d is going to be equal to our V, our 4.5 times, we need to be careful with the units because this is kilometers per second. We want to cancel on this to leave us with megaparsecs. So let's take a 10 to the 3 out of this and make that 10 to the 4. So we've got our V in kilometers per second. And then we need to divide by our Hubble constant of 65. And then that will give us the answer in megaparsecs, which comes out at 692. So let's say 700 megaparsecs to, well, I mean, that is two significant figures. They have given us 65 here. So yeah, two significant figures all round. Estimate the age of the universe in years. Right, this is just about making sure you get your units right. We know that the age is 1 over the Hubble constant. So, and we want to get this into years. They've given us seconds in a year. So let's get our Hubble constant into just seconds to the -1. Let's get rid of these kilometers and these megaparsecs that we've got here. So we need to take our h0 and then say that that is 65. We need to then multiply by 10 to the 3 and divide by the megaparsec. So that's 3.1 times 10 to the 22 for a megaparsec. So we have to add an extra 6 on the power there. That's giving us 2.1 times 10 to the -18. That's seconds to the -1. So that can then give us the age. We just have to flip that, take the reciprocal of that, but then we need to turn it into years. So we can say the age then, reciprocal of this is giving us 4.77 times 10 to the 17 seconds. Now divide by seconds in a year, and that then gives us 1.49 times 10 to the 10 years, which is what, 15 billion years, give or take. So let's say 15 billion years, which is about what we'd expect. A little on the high side, but that's fine as a calculation. Last part, the age of the universe is calculated from the time of the Big Bang. Describe 2 observations that directly support the idea of the Big Bang. Right, well, we're already in the world of Hubble's law, so let's go off of that then. So we can say that the spectra of galaxies suggest that they are moving away from us. Suggest that they are moving away. I don't know why I'm writing all this out. I might just say it. Then again, whenever I say that, I always write it out anyway. Spectra of galaxies suggests that they are moving away from Earth. from Earth, and this is based on, so you could add on there, based on the change in wavelength of spectral lines. So then put in bracket maybe redshifts. Don't just come in and say, oh yeah, there's redshifts. Like, flesh it out a bit more. Put something fuller as an answer like this. So that'd be one thing you could say. You could stay in Hubble's law and then say another one, and say galaxies that are farther away seem to be moving faster away from us. Farther away are receding more quickly. Receding. That's got too many E's, isn't it? Receding faster. So we've got too many options out of Hubble's, but it might be best just sticking with one of them out of Hubble's law, just in case they start getting funny on the mark scheme. Do something different. The one that's always the go-to is the existence of the cosmic microwave background radiation. Of cosmic microwave background radiation, obviously write it out in full, which is, you could say, isotropic or same in all directions. Same old thing, isn't it? Same in all directions. So you could do a variation on that about the temperature. Say that the temperature of the universe is currently 2.7 Kelvin, as predicted by Big Bang theories. So you've got, that's 4 options there. So you've got plenty of choice when it comes to, going through supporting evidence for the Big Bang. Some people start getting into the primordial helium one. That's another one that's fine. I just go to Hubble's and the background radiation. They just seem to be the simpler options on these. Right, second question. Define the parsec. Draw a diagram to illustrate your answer. Right, simple enough diagram. So starting from, we've got our background stars. We've got our nearby star. We've got the sun. And we've got the Earth in 2 extreme positions in its orbit. We can then draw in some dotted lines. So we've got that dotted line there. We've got this one. I knew one of them was going to go wonky. Then we got this one all going through the nearby star that we've got here. So from the 2 extremes of the Earth and the sun, then we mark stuff on. So the distance from the sun to the Earth, 1 astronomical unit. You could label these things as well, I suppose. Sun, Earth, capital E for Earth. And then star, background stars. So write them all on, Then we've got the parsec we want to mark on. So that's the distance from, it doesn't matter whether you're drawing it from the Earth or the sun, it's all the same really, up to the star. So that is 1 parsec. And then we need to mark on an angle. And you can mark any of these. You could do this one, this one, this one, this one. It doesn't matter. They're all the same angle. So you mark on one of those. And I'm going to pick this one here and say that is 1 second of arc. So that's your picture. The star Tau Ceti has a parallax of 0.275 seconds of arc. Calculate the distance from Earth in parsecs and in light years. Right, this is how we're doing these calculations off of here. We're doing this small angle, really. Tan theta equals theta for small theta, small angle. So when we're looking at 1 second of arc, we're saying, okay, we've got 1 second of arc is 1 astronomical unit divided by 1 parsec based on this setup that we've got here. So if we've now got 0.275 seconds of arc, that's still 1 astronomical unit divided by some other distance that we've got here. Obviously, as this increases, as we increase our distance to the nearby star, these angles are getting smaller. So we got our distance is then 1 over 0.275, which is 3.64. So, and I've given it, they've given it to, given it the 3 decimal places there, 3 significant figures. So yeah, let's leave it at that. That'd be fine. Then we've got the in light years. We just need to change this to light years. They've given us what a parsec is. So we can turn that into meters just by multiplying it by 3.1 times 10 to the 16. So that gives us 1.127 times 10 to the 17 meters. Now we need, if we want to get this into light years, we're going to have to divide by the distance that light travels in a year. So 3 times 10 to the 8 is our speed of light. That's our meters per second. Multiply by seconds, we get meters. So 60 by 60 by 24 by 365 and a quarter. Multiply all that together and then stick it on the denominator underneath this, which is coming out at 11.9 light years. So fairly simple question, that one actually, but it's a nice recap just to make sure you can do these basics, to make sure you really understand this diagram and how we're putting parsecs together. All right, let's wrap up with this question then. Describe the formation of a star such as our sun and its most probable evolution. Right, part of this we covered in a previous question, but it can't do any harm to sort of run through it again and then add on the bits at the end. So I'm going to do all of this in shorthand because it will just take up far too much space otherwise. So we're starting then with our dust and gas cloud, or clouds. So that's where we're beginning. So start off with that. Then we're getting gravitational contraction of that. So gravitational contraction. This is taking gravitational potential energy down, kinetic energy up, temperature up, and then eventually we are going to get fusion of protons into alpha particles, or just put hydrogen into helium. So that's what we're getting there. Then we're getting our stable star part of it. So we've got a stable star when we've got the inward forces equal to the outward forces. So we want to say in equals out essentially in terms of forces. So this is gravitational force inwards is going to be equal to various pressures on the outwards force. So we've got radiation pressure, we've got thermal pressure going outwards. So that sets us up as a stable star. Then we get to a point where the fusion slows or stops, at which point we get core contraction and expansion of the outer layers. So we'll get a new bout of fusion going on. So this gets the temperature up. This gets a new fusion. This is where we get the shell of fusion around the core. The expansion of the outer layers, this takes us to red giant phase. And then eventually we will lose the outer layers of the star. So outer layers lost, and we end up as a white dwarf. So that's what we've got in shorthand for this formation of a main sequence star and subsequent evolution. You don't have to have every single part of it, but it's about that contraction, heating up, start fusion, become stable, fusion stops, so we contract again, start more fusion, expand, red giant, lose the outer layers, white dwarf. Describe the probable evolution of a star that is much more massive than our sun. So we've got the same stuff going on here really, but the difference is when we've got the more massive stars, we're getting fusion of heavier elements. So that is one part of it. And then we've got the final part of the evolution, as in we've got supernova, and then we end up at neutron star or black hole. So you're just wanting to turn those into sentences rather than shorthand, but 2 or 3 of those will then get you the marks for that. Right, part B. Present mass of the sun is 2 times 10 to the 30 kilograms. Sun emits radiation at average rate of that. Calculate time in years for the mass of the sun to decrease by 1/1,000,000th of the present mass. So what is 1/1,000,000th of the mass? So where am I going to put this? Let's stick it down here. 1/1,000,000th of mass is, well, it's just that divided by 1,000,000. So that's going to be 2 times 10 to the 24 kilograms. So we need to get this from our conversion of mass to energy. So we've got our E equals mc squared. So that means that E is going to be 2 times 10 to the 24 times c squared, which is 9 times 10 to the 16. So that's a lot of energy. That's what, 1.8 times 10 to the 41, since I pinched one from the 18. So that gives us our E. So we now want to get this into years based on this power output that we've got here. So if we divide, because that's joules, so let's divide our joules by joules per second, will give us seconds. So divide by 3.8 times 10 to the 26 joules per second, joules per second. So that comes out at 4.74 times 10 to the 14 seconds. And now we have to get that into years. So we divide that by seconds in a year, 3.2 times 10 to the second seconds per year, because that's what this is here. And then that gives us 1.5 times 10 to the 7 years. So obviously set these out on a few more lines in your calculations rather than doing this shorthand that I'm doing here, just to save space on the screen. But the process, you can just see what's happening here. It's all unit driven as well. If you can't quite see where to go, if we've got some joules and you want to get seconds, divide by power and you're going to be getting some seconds. So just keep an eye on your units all the way through and you'll be fine. Last part of the question, C. Following nuclear equation summarizes a typical fusion reaction cycle that occurs in the sun. So 4 protons into a helium nucleus, a couple of positrons and a couple of neutrinos. Explain the process of nuclear fusion in the core of the sun. In your explanation, refer to the conditions necessary for fusion to occur. Again, they're not looking at loads of detail here. You can actually get a mark just for talking about that equation and just saying what's happening. So I'm going to again have to put this in shorthand, but we're getting protons going to helium nuclei plus positrons plus neutrinos, which is just a statement of what they've already given us. And yet turning that into words rather than just that equation, and they give you a mark for it, which is interesting. So we've got that, but the key features all of this for the necessary conditions. So we've got electrostatic repulsion. So keywords there, electrostatic repulsion between the protons. So we need high temperature, high density, high pressure. High temperature, high density, high pressure for fusion to occur. If you can get them close enough, this is the thing. If you can get protons get close enough under those conditions for the strong nuclear force, so you certainly want to be mentioning that somewhere in your answer, to bind them together. Then we've got the greater binding energy. This is one last bit you could put in. So greater binding energy, that means we've got an energy release. Leads to energy release, which is where it's all coming from in nuclear fusion. So that's that bit. Several points there. I mean, that's 1, 2, 3, 4, 5 points there on that. I mean, they're not going to have 5 marks for a sub question, but you've got loads of options there for picking up your marks. Name 2 forms of energy produced in thermonuclear reactions, where you've got kinetic energy. All of the products have got kinetic energy. We've got electromagnetic energy because we've got loads of photons that are being produced. So you could just say photons or electromagnetic energy, but there's 2 forms. Last part, binding energy per nucleon of a proton, well, that's going to have 0 because it's not bound to anything, and a helium nucleus are 0 and 7.2 mega electron volts. Calculate the energy produced in joules for the fusion reaction above. So we're binding 4 nucleons into this helium nucleus. So we're going to have 4 times 7.2 mega electron volts, because this is binding energy per nucleon. So that's going to be 28.8 mega electron volts. They want it in joules, so easy enough. We just have to multiply by 1.6 times 10 to the minus 19. Don't forget we've got a mega here in mega electron volts, but that's going to convert it into joules, which is coming out with, I've dropped off the bottom of the page, so I'll write it up the top here, 4.6 times 10 to the minus 12 joules. So yeah, there you go. That was a nice little calculation taking us back to our nuclear physics days, just to wrap that one up. So that was a nice trio of questions.